this will be an introduction. And since it's the first talk, I figured that I would introduce oscillations from a historical perspective. And most of these things I expect you to know. But I think it's good to set some common tone. And then I'll talk about a little bit about things which are specific to supernova environments, time permitting at the end. So, as I said, the plan is to do oscillation physics 101 with a tilt to historical perspective. And then I want to briefly mention things which are relevant to neutrino transitions in the supernova-like environments. And then there are several talks here, so who are you and JJ, and I think somebody else will give details on how these calculations proceed and what are the supercomputing requirements and how you optimize the calculations. This is primarily not a supercomputing talk. So it's a good thing to show this picture. So the Symmetry magazine, which is kind of a popular magazine in particle physics, has neutrinos finally as their feature story. So this was last year. And they have this cute kids puzzle, which shows that the neutrinos don't really fit neatly with the rest of the particles. And the first question to interested students is, there is a small but important technical inaccuracy in this figure. And so ponder what this might be. So I will show this, and I'll return to this in a few slides. So historically, one thing to mention is that neutrino physics has progressed dramatically over the last 20 years, really dramatically, in both experimental and theoretical directions. But experimentally, you can just convince yourself by going back to the old particle data group reviews and looking up how things changed. So here is an excerpt from 1996. And the summary, and this is 18 years ago, so this is not that unusual or not that distant. And they say no direct uncontested evidence for massive neutrinos or lepton mixing has been obtained. And then there are some limits. So then 2 years later, what is this? 2 years later, they say, while no direct uncontested evidence for massive neutrinos, oh, okay, I don't know. This is too complicated for me, maybe. There we go. No? Okay. While no direct uncontested evidence has been obtained, suggestive evidence has come from solar neutrino observations from anomalies in the relative fractions of nu e and nu mu observed in energetic cosmic rays, cosmic ray air showers. So these are atmospheric neutrinos, and possibly from nu e bar appearance experiment at Los Alamos. So the last one we are still grappling with. So you can go and look at these links and see. So they have some information on solar neutrinos and atmospheric neutrinos. And then 2 years later, they say that there is a rather convincing evidence that neutrinos have non-zero mass. So, you know, it's really amazing to look at this progress issue by issue, because for comparison, things in particle physics go on a much slower time scale. Now, here is a plot from a review in 1998 on the precision electroweak data and what that meant for the mass of the Higgs boson. So there are direct, indirect measurements at LEP and at SLAC at SLC, and they were favoring some region of parameter space in the MWM top plane. There are stripes here, which you probably cannot see, corresponding to different Higgs masses. And you know, as of now, we know that the Higgs is here. So you can see how remarkable the data was already at that time. Now, it would be wrong to conclude that my mission here is to say that the Higgs discovery was unnecessary or anything like that. What I'm saying is that it is very difficult in particle physics, in modern particle physics, to make these qualitative steps. They take decades, and on that time scale, the neutrino discovery, you know, really developed dramatically. So one thing that I want to ask here, another basic question, is what is called a particle? So a particle, if you talk about an electron versus a muon versus the tau lepton, for example, you say, well, they have the same gauge interactions. But they are clearly different because the electron is much lighter than the muon, 500 times lighter. And the reason for that is that, well, okay, they're both eigenstates of given masses, and this eigenstate is much lighter than the other one. In terms of interactions, you can take any linear combination and it will have the same interactions, but what you call a particle is an eigenstate of mass. So before the discovery of oscillations, neutrinos were the only particles defined as their flavor eigenstates, which meant that there were particles that couple, states that couple to charged leptons through the W boson. So they were the only weird guys. So you have some space of charged leptons, and the W boson then couples them to some superposition of these neutrino states, and they were called nu e, nu mu, and nu tau. But now we know that what neutrino particles are, that there are three distinct mass eigenstates, and interestingly, they don't okay, and they have been given very imaginative names, nu1, nu2, and nu3. So people working in this field have terrible PR problems. but at least, you know, the important message is that there are neutrino particles, mass eigenstates, and in terms of these original flavor eigenstates, they are large mixtures of those states, which is unusual. In the quark sector, we don't have that, large mixtures. So if we go back to the symmetry magazine feature, and you see the quarks here are down S and B, not D prime, S prime, and B prime, which would be flavor eigenstates coupling to these guys. So here, what they needed to have is nu1, nu2, nu3, but that was too unsexy, so I understand. So neutrinos have masses, but other particles also have masses. So perhaps there is nothing unusual that we discovered some masses for these particles. What is unusual is that, you know, these masses are weird, right? They are much lighter on the logarithmic scale. The neutrinos are much lighter than the other measured particles. And not only that, but they interact through the weak interaction, which is energy dependent, and it decouples at low energy, which is a property of it being non-normalizable effective operator at low energy. And the problem is you can't slow them down easily. So for all other particles, we can slow them down and measure them in some precision experiment. Well, in the case of the top quark, for example, we don't slow them down, but we look at the branching ratios and construct the energy. For neutrinos, they're stable, so in principle, we would want to slow them down and measure, but we cannot easily do that because they become more and more weakly coupled. And so then we need extraordinary measures. And one, you know, there is sort of a list of a few basic ideas for these extraordinary measures. So we could consider a decay process where you create a neutrino and very carefully measure the endpoint spectrum of such a decay process. And this is what happens in the decay of tritium, where people are trying to see how the spectrum ends with great precision and trying to measure the neutrino mass from that. But it is a very experimentally demanding measurement. If you have Majorana mass terms, they violate lepton number. And so you can look for very rare processes that violate the lepton numbers and neutrinoless double beta decay. And you have these precision experiments, EXO, Majorana, and Gerde. Then you can use cosmology, so you can slow down your neutrinos by redshifting their energies and then use gravity to detect their effect. And there is a whole field, which is right now very exciting and very active. You look for a combination of precision CMB data on large-scale structure, lensing of CMB, and that, you know, currently is giving the best or very stringent bounds. There is an asterisk to this that they require understanding of your cosmological models, but they're in principle very sensitive to neutrino masses. And the last but not least is you can use interferometry. Every time you have something small, you can try to use interferometry. So oscillations are in this last category. So the idea is I don't know. The idea is very simple. So you create your particle in a superposition of some two states. Then you let this state evolve for some time. And then you measure. And there is a relative phase that accumulated in one state relative to another because there is an energy difference between these states. And that's what we do in optics, and that's what we do with neutrinos as well. So in neutrinos, the usual argument is you take the energy expression for the neutrino Hamiltonian, you expand it, and you say some words like these states are produced with the same momentum, and then there is a difference in energies, which gives this oscillation phase. So when you have neutrinos propagating through vacuum, you can find your delta E and corresponding oscillation frequency by doing this. Sometimes people say you have to assume that they have the same energy, and then you do expansion and momentum, or sometimes they say you have to assume the same velocity. There is a lot of confusion about that. It's neither, actually, because what you need to do is you look at the process, like, for example, in the sun, you have this boronate nucleus, which can decay to beryllium-7 positron and a neutrino, and you know that you have 3 neutrino states which have slightly different masses. So you consider 3 of these amplitudes, and you do the kinematics, and because you know these guys have slightly different masses, then you can convince yourself by looking at this a bit more carefully that there is a phase difference between these 3 outcomes, and the phase difference is indeed given to very good accuracy in the outer relativistic regime by this term. So if you want to think about something as an exercise, show that this expression is valid when you consider this process more properly. And you know, the second question that you might want to think about is, it seems like if we just measure the energy of this neutrino very accurately, it's enough to decide to which state it went. So how can this be consistent with flavor oscillations? And of course, the solution is to think about the uncertainty principle, and accurate energy measurement breaks the position measurement. So it is easier to think about pion decay, for example, but the 3-body, even if you fix the differential process, that they all go in the same direction, then and this, I bring this up because I want to talk about solar neutrinos in a little bit. But in principle, people every now and then rediscover, you know, how to do this properly, and the learned people write papers that they discovered how to do this. But it's a good exercise for every student at some point in their career to think about these things, how you get oscillations, taking into account uncertainty, energy uncertainty, and so forth. I just bring this up as a warm-up. What we know now is that there are 2 mass splittings that have been measured quite well. They're shown here. One has a label atmospheric, and the other one has a label solar, factor of 30 different. And there are 3 mixing angles, which are measured now. This theta 1,3 angle has been measured only very recently, and it went from unknown to the best measured angle in a matter of a year. So it's quite remarkable that we know theta 1,3 now better than other things. And within this picture, we know that there are several unknowns. We don't know the ordering of the states, called the mass hierarchy. We don't know the CP phase, and we don't know the nature of the neutrino mass. And of course, beyond that, there could be new physics effects, sterile neutrinos or additional interactions, or sterile neutrinos with additional interactions, and so forth, where it's important to go to the next level and measure oscillations and other neutrino properties very precisely. But at least this is a snapshot, this situation did not exist 15 years ago. So very briefly, if you want to understand these numbers on the masses, you can ask yourself, what are the relevant scales here? So if you take an atmospheric neutrino of a few GeV energy, then you put the typical energy and the splitting on the previous slide, and you find the distance scale of 10 to the 3 kilometers, which is a very good distance scale to probe on the scales of the Earth. So this is why atmospheric neutrinos were suitable for this problem. SuperKamLAND looked at the zenith angle distribution of neutrinos at different energies. Stopping muons were at lower energy, and at higher energy, their muons enter the detector and exit on the other end. And they saw that there was a kind of a smoking gun signature of oscillations, that things vary with the mixing angle, where things that go through the Earth are more suppressed. And this convinced actually the world for the first time that there were oscillations. Now, skipping a decade, so for reactors with a few MeV energy, for reactor antineutrinos, you can again do this exercise and you find that, this distance scale is about 10 to the 2 kilometers, which is a good distance to study on the scale of Japan, which is where the KamLAND reactor ran, and it has the most precise measurement of delta M squared. So you have the unoscillated spectrum, and then you have this measured spectrum, and this measured spectrum is clearly showing energy-dependent suppression, which is consistent with neutrinos oscillating. Now, the third distance scale is that you have reactor antineutrinos. They have, again, energies of a few MeV, but now you divide by the bigger splitting atmospheric, and then instead of 100, you get the distances of a few kilometers, and these are good distances to probe if you park your reactors close to a power station, and this is how Daya Bay and Reno have discovered this theta 1,3. I'm not sure what's happening. Okay, there we go. Theta 1,3 mixing angle. Okay. Now I want to talk about solar neutrinos, since my task here is to talk about neutrinos and astrophysical objects. Then there is a case where we measured the neutrino flavor transformation process with considerable precision. And this is actually the place where the first neutrino oscillation effects were detected. But it was very hard to prove that they were neutrino oscillation effects. But they were detected as early as 1968. Tony talked about 1960s as being the start of the supernova physics. And also for neutrino oscillation physics, 1960s were the time when it all started. So there is this remarkable experiment, or there was this remarkable experiment in the Homestake mine, which was 100,000 gallons of dry cleaning fluid somewhere deep in the mine at the 4850 level in this cavern, which now has the LUX dark matter detector. And every few weeks, Ray Davis and his team would extract argon atoms, which were formed by this reaction from the sun. They had a prediction of 50 atoms or 51 that would be created in the tank, and they only saw 17. So you can go to the website of BNL, and there is a historical press release from this first measurement. And the press release is very nice. It says that there were these solar neutrinos detected for the first time. And there is, interestingly, no mention of oscillations whatsoever. So what they said is that the theoretical forecast had led scientists to believe that the neutrino emission from the sun would allow 1.5 to 5 neutrino captures per day. Notice that there is a huge error bar. It wasn't like that in the original papers, but they had to sort of make them bigger. Dr. Davis reports that the capture rate in the underground tank was less than 2 neutrinos per day. Knowing this, plus the efficiency of the neutrino capture, allowed Dr. Davis and his group to calculate the flux from the boronate decays to approximately 60 million solar neutrinos per square inch per second at the Earth's surface. Previous calculations had predicted the flux could be anywhere from 40 to 150, and basically the message is that now theorists will adjust their models. It's quite a remarkable document. I mean, of course, it would have been very striking at that time to understand that these were neutrino oscillations, but nonetheless, sometimes being conservative is not the same as being right. So the history of this subject is that there was this detection, and most people said that the solar model needed to be adjusted, but some persevered. So in 1978, a decade later, Lincoln Wolfenstein pointed out, by analogy with kaon regeneration, that the presence of matter, background matter, would impact neutrino oscillations, and it would then, so coherent forward scattering, which is the same physics of index of refraction, would be, coherent forward scattering would cause the medium to be birefringent to neutrinos. So nu e's had different interactions from nu mu and nu tau. And then Lincoln argued that this would suppress oscillations in the core for a broad region of parameters. The paper has an incorrect sign and an incorrect factor of 2, but those are details. The thing is that the magical or the really remarkable thing is that the equations are basically written down for the oscillations, but they're not solved. So they're not solved. There was a changing solar profile in which this equation should have been solved. And instead, there is a comment that the core does not have neutrino oscillations. But, and this I think goes well to the topic of this workshop, sometimes it really helps to solve your equations, numerically or otherwise. And it's a very similar scenarios played out for the history of collective oscillations and supernovae. The Hamiltonian had been known for some time, and only when this problem was studied numerically properly, it was found that there are unique large flavor transformations. A caveat or a footnote is that a large part of this paper that Lincoln wrote was actually on possibility of new flavor changing interactions. And this question we're still grappling with, whether there are new flavor changing interactions in the neutrino sector. So then Mikheyev and Smirnov, they didn't know that they weren't supposed to solve these equations, so they solved them. So they found that for some parameters, there was a large conversion, possible even with small maximum vacuum mixing parameters. This is very interesting. What happens next? Because they submit this paper and it gets rejected. You can go read this, the history in this more recent preprint that they submitted the paper. They used the word resonance for conversion. The paper is rejected. Then Mikheyev and Smirnov repackaged this problem, hiding the word solar, talking about supernova neutrinos instead, and hiding the word resonance to page 3. Then eventually this gets published and then immediately recognized. So the MSW phenomenon is then suddenly accepted by all people who practice neutrino oscillations. And there are two reasons which are very persuasive to people. One is that you could get large conversion as seen in the solar experiment, even given the small mixing angle. And there was a consensus or a very strong bias that neutrino mixing angles would be small naturally, just like in the quark sector. And second is that this mechanism of conversion was very generic because the density profile in the sun spans several orders of magnitude. So you can get this resonance depending on what your delta m squared is here or here and so forth. It didn't matter. Now, it's curious also to notice that the large high energy community, the bigger high energy community remained quite skeptical to this. So this is an opening to the paper by Georgia and Luke in 1990, which is, you know, quite a bit recent. It starts most likely the solar neutrino problem has nothing whatever to do with particle physics. It is a great triumph that astrophysicists are able to predict the numbers of boron-8 neutrinos coming from the sun as well as they do, so within a factor of 2 or 3. And then they say, oh, but you could have a neutrino magnetic moment, and that's interesting for a particle physicist. So then the rest of the paper is on that. Now, in the hindsight, we can, of course, laugh, right? Because the solar mixing angle, in fact, turns out to be large. And this argument, this bias that you should have a large conversion for small mixing angle is not realized. So the hierarchy of small angles, which is seen in the quark sector, is not present in the lepton sector at all. And then there is a fine-tuning in the solar data. The mass squared splitting in the solar data turns out to be fine-tuned to the matter density in the center of the sun. So that I want to talk a little bit about. So what experiments measure is they measure neutrino conversion probability at different energies. The higher energies are best measured because you have SNO and super K doing this with great precision. This is the SNO measurement of the spectrum. And at lower energies, this is Boric-Sino. And here you have other fluxes inferred by gallium radiochemical experiments, the PP flux. And the message here is that there is a change of the survival probability over the range of solar neutrino energies. And that's actually quite non-generic. Generically, you'd expect one number. So something happens physically as you transition from sub-MeV to multi-MeV energies. And what happens, as we understand it now, is that the matter density in the sun is such that the potential the MSW potential is equal to the vacuum potential for a typical neutrino energy of 1 MeV. So fine-tunings happen. Okay, now solar neutrino oscillations. I assume that you've seen this before, so I'm not gonna say very much about it. It's basically a quantum mechanics problem where you have a state of several components, 2 or 3. So there are, if you have 3 flavors, then this is a 3-flavor state. There is a Hamiltonian, which is a 3 by 3, which has a vacuum piece, which has these delta m squared over 2e, and then a bunch of mixing angles in them. So it just tells you how you rotate from flavor eigenbasis to mass eigenbasis in vacuum. And then in the presence of matter, due to this coherence, I don't understand this. Due to these coherent scatterings, you get an additional term which singles out electron neutrinos, and it's proportional to the background density of electrons. So then in matter, you have to rediagonalize your Hamiltonian, and your Hamiltonian eigenvalues change as you go to deeper matter. So in vacuum, you have these 2 splittings, and then when you add the third term, then this eigenvalue changes, which is schematically shown here. Now, the idea is very simple. If you do a 2-state oscillation problem, then you can just require that neutrinos, the evolution is adiabatic, which means that if your neutrino finds itself in this state, then it doesn't jump to the other state, it just stays in this state. You create a neutrino, electron neutrino, you project it on the basis of eigenstates in the center of the sun, and then you project it back in vacuum, and this gives you the conversion probability. So this is the expression for a 2-flavor survival probability in the sun. These are just, sines and cosines from the projections. The physical ingredient here is that I said that there is no level jumping, and to do that, I need to have a certain check between the relevant distance scales. So the oscillation distance scale has to be significantly shorter than the scale on which density changes. So there is a scale height which you get as a logarithmic derivative of density, and that the oscillation length has to be shorter. So the system wants to oscillate faster than the rate with which the Hamiltonian changes. You can convince yourself of that this is so. And the idea is that for most of the sun, the density scale height is roughly 1/10 of the solar radius, and the oscillation scale is comparable to the width of Japan because it was probed in KamLAND. So 100 kilometers versus 1/10 of the solar radius. So you convince yourself of that. Another thing is that when I wrote this equation, I left out the interference term between these 2 states. And there are several ways that this interference term disappears. For example, if you consider that the region has a finite production size, again, the size of the production region is much bigger than the neutrino oscillation length. So the phases average out in that way. But you should think and convince yourself of that. Okay, so now we have 3 states, actually not 2, but the third state is very easily taken into account because in the center of the sun, this correction due to the presence of matter is comparable to the splitting between these 2 states, and this state, this splitting, which is 30 times larger, is basically not affected by this matter potential. So then there is a small probability that your electron neutrino gets projected into this third state, and then it remains in this third state, and then you repeat your 2-flavor oscillation formula, and then you have this sine to the 4th here of theta, and it's a very easy thing. You just convince yourself that the projection on this state is given by the sine of theta 1,3, which has been measured. So given the measured value of theta 1,3, this gives like a 4.5% correction to the 2-flavor survival probability and overall deficit. And the deficit is easy to understand because when you go in that state, you're basically gone. So, okay, that's the 3-flavor effects, very easy. Now back to the data. So I have this expression where I have cosines and sines in the center of the sun. If I'm dominated by matter in the center of the sun, then I find myself in this regime. And then if matter doesn't matter, then I find myself in another regime. And this basically is averaged vacuum oscillation. And this is classical MSW. It turns out that the fit tells you that for low energy, you have standard MSW, standard vacuum oscillation with these sines and cosines to the fourth. And here you have sine squared theta 1, 2. And it's, this is the way this works out is because this transition happens right in the middle of the energy range of solar neutrinos. So, by the way, comment on fine-tuning. If this sounds very fine-tuned, it used to be 14 years ago that there were other solutions allowed. So there was this small mixing angle, which people had a bias for, and there was also this region of vacuum oscillations. In each of those cases, there was something fine-tuned to something. So for vacuum oscillation, the oscillation length was fine-tuned to 1 astronomical unit. For the small mixing angle, it was that you had to be fine-tuned to be on the adiabatic, non-adiabatic boundary. And then for this region, you imposed the resonance in the Earth. In any case, to get energy-dependent signals, something had to be fine-tuned. Nature prefers this solution that you are here. Okay, before I go to supernova, I want to describe this picture since it will come up many times, no doubt, in the discussions of the oscillation phenomena. And that is that if instead of thinking about Hamiltonians in quantum mechanical sense, you can just picture this process as an evolution of a spin. This certainly is completely straightforward to do. You just plot an expectation value of your spin. And if you're doing 2 flavors, any SU2 system can be depicted in this way. If you do 3 flavors, then you use Gell-Mann matrices, so you have an 8-dimensional space. It's kind of hard to visualize, which is why this spin is useful for a 2-flavor system. So the idea is that you have an oscillation Hamiltonian, which you can think of as some vector h times the sigma matrices. And so this is an external magnetic field multiplied by a spin. So this is a spin in an external magnetic field. The magnetic field changes because the Hamiltonian changes because the matter density changes. So you start out in the case where matter dominates. The Hamiltonian is aligned with an electron neutrino direction. And then as you relax to the vacuum Hamiltonian, this spin, or this external magnetic field, makes a rotation to some other direction. And if this rotation is sufficiently slow, you can just see that explicitly in the solution, then the spin just rotates around it and follows. So that's the graphical representation of what the MSW effect does. It's just a relaxation from adiabatic relaxation from strong coupling to weak coupling. Okay, now I want to talk about supernova in the time remaining, but I want to know if there are questions. This was basically a review, but if there are any pressing questions, I'd like to answer them. There are no questions. This is all well known. Okay, so now in the supernova case, the problem is much richer and much more interesting, both in the theoretical sense and in the computational sense. And the process of flavor transformations in this case is still not understood. But I want to show some ingredients. So Tony talked about the central region, which is this inner 10 or 20 kilometer region emitting neutrinos with a neutrino bulb as a source. These neutrinos are emitted in all flavors, generally with different spectra. And then here they stream out freely and they undergo coherent transformations. In the case of this plot, they undergo 2 resonant transitions at large radii corresponding to the regular MSW effect. So in the sun, because the density goes only up to 10 to the 2, you have this resonant transformation only. Here, because the center is very dense, you go through a much broader range of densities. So also the solar splitting has a corresponding resonant density. And then at the very least, you have to do your MSW transformation twice. Then in addition to that, you have this profile which changes as a function of time. So this front shock is moving out. This corresponds to a snapshot of about 1 second in time. This front shock is moving out. The region behind this shock is actually not as neat as shown in this 1D simulation, but it is turbulent, as I will show. And then you have to do your MSW effect in this turbulent region. And then, to top it all off, there is a region closer here where you have collective oscillations, where neutrinos provide MSW background for other neutrinos. The density of the streaming neutrinos is so high that when you look at the oscillation Hamiltonian, they enter into each other's Hamiltonian. And the system is no longer a single particle system, but it's an n-body problem where different energies and trajectories are coupled. So this makes it very interesting, as I mentioned, theoretically and computationally. I'll start with sort of the easier to explain first. So if you have a shock, which as shown here moves as a function of time, then on the time scale of several seconds, it will arrive to the resonant density, and it will change how your flavor transformation at the resonance occurs, as was first pointed out by George and Richard Shurato, who was a student at UCSD at that time. And this is a very nice signature to look for in the detector because it has a unique time dependence. If you detect something like this, then you can say that there is a physical phenomenon that is not easily explained by things at the neutrinosphere. So I will get back to that later, but this is the idea. So the idea is that before the shock perturbs the MSW resonance, this profile is smooth because it corresponds to the density gradients in the progenitor, and the progenitor star is a polytrope, and the polytrope has the scale height, which corresponds to the value of the radius. So here, if your radius is a few times 10 to the 9, then the scale height is about 10 to the 9, and that is much bigger than the neutrino oscillation length, which is on the scale of Japan or less. So then you can see that the evolution has to be adiabatic. When the shock arrives, the width of the shock has to do with the photon mean-free path or something like that, which is much less than the neutrino oscillation length. And you get a step in your density profile, and the evolution becomes non-adiabatic. So you can make a plot of levels schematically, like I've shown here. So you have different components of your initial emitted spectrum. You have electron neutrinos and mu and tau, where electron neutrinos are generally thought to be colder to begin with. If you have this transformation adiabatically, where these electron neutrinos are swept into the third state, which has very little of electron neutrino in vacuum, then what you measure as electron neutrinos on Earth comes in these two states, which came from mu and tau. And what you're measuring as electron neutrinos are actually the Hata spectra of mu and tau. But if your shock perturbs this picture, then your electron neutrinos sip in, or they come in, and they generally cool your spectrum. And it's a time-dependent feature that you can look for with detectors. So if you don't see it, I'm happy to explain how this works later. But basically, the electron neutrino that you observe in vacuum lives in these bottom two states. And if you can jump levels, then this colder component comes in. Okay, now that's the first complication, but it's certainly not the last, as I mentioned. Because if we look at the simulations, and this is a beautiful simulation from the Oak Ridge group, which is available online. This is the simulation that discovered the SASI instability. For the purpose of this talk, however, it's interesting not just what happens at the shock, but what happens behind the shock. What happens behind the shock is that the density is completely turbulent. And then when this bubble expands, you have neutrinos propagating through this expanding turbulence. And that's what you have to treat. So instead of having a smooth profile, you have these density fluctuations where neutrino encounters a very, very bumpy ride. Now, I cannot resist this temptation to show this. People have studied this later in a backyard experiment with sloshing water and found that for certain conditions, this beautiful SASI instability can exist in your backyard. I have to, let me see, there. So this made the cover of PRL. And because there is this sloshing that causes modulated accretion rates, you can look at that in the signal at large detectors like IceCube, where the rate of events could be modulated by the sloshing SASI. So this was suggested as a signal for IceCube, and I think this is a very neat idea to see the imprint of this physics directly in the terrestrial data. Now there are other groups which simulate these explosions with different assumptions. So now this one has central heating, but as I understand has hydrodynamics, which is not nearly as good. But the common feature is that you have these large plumes, and these large plumes clearly show well-developed turbulence. And as the explosion is pushed out, these plumes persist, and neutrinos have to travel through these plumes. Now, from the point of view of neutrinos, you need to understand how to treat this. And it turns out, and you can show that, I don't have much time to go into this, but I want to give you the basic picture. The basic picture is that the relevant scales of fluctuations are small, smaller than what is resolved in these typical simulations. The relevant scales have to do with 10 kilometers, which is the neutrino oscillation scales. So you have larger fluctuations, which your neutrino is able to follow adiabatically. And then you have these oscillations, these fluctuations on smaller scales, for which you need to know the power spectrum. So then you can do this analytically. I don't go into that. You have an integral over the spectrum of fluctuations with some response function. This response function has to do with the wave number scaled to the neutrino oscillation length as advertised. And the response function is basically, it's a theta function. For longer distance scales, you follow fluctuations adiabatically. For shorter distance scales, it's suppressed by a power law. So what you need to understand how the turbulent fluctuation impacts your signal is you need to know the spectrum of fluctuations on scales of 10 kilometers and below. Now, again, in this picture of flavor spin in a two flavor, you can view this process as diffusion on the flavor sphere. So you have several realizations of turbulence, and they basically, you have a magnetic field that keeps shaking around. It diffuses the spins over the sphere, and in the limit where you have a lot of shaking, they just spread out all over the sphere, and in this case, the answer is known. Now, if we take what we know about the simulations, we can take large-scale fluctuations and then assume that there is a Kolmogorov-type cascade to smaller energies. The dissipation scale is much smaller than the scale of neutrino oscillations. So this cascade is in the inertial regime. And you can take large-scale fluctuations of the published simulations, which are order 1 fluctuations on the scale of the bubble. And then you scale them to smaller scales, and then you get that these small fluctuations are strong enough to cause complete flavor depolarization. But what we would like to do, of course, we would like to check if this is indeed so once we have sufficiently large simulations from people who simulate this. So there is a request to people who do supercomputing to try to run their simulations with as high resolution as possible for several seconds. Because normally they declare victory the moment they see things explode. But it's very interesting to know how this turbulence that vigorous turbulence that was created during the first second, how that then evolves in the expanding bubble. I know. But, you know, this is one of those effects which could be imprinted on the signal. So I think it's worth it. I've been trying this for several years. The bottle of wine hasn't worked yet, so. Now, for the last 10 minutes, I'm going to talk about this magical phenomenon of neutrino collective oscillations. And I just want to touch on it because there will be talks later, and I just want you to understand what's going on. So what's going on is you have a neutrino propagating in the sea of other neutrinos. So from the point of view of this neutrino, the other guys are a background. And if the other guys are a mixture of electron and muon neutrino, sometimes you can have this process where this neutrino scatters on a background neutrino, and they exchange momenta. And this process can be coherent, right? So from the point of view of this neutrino, it travels through the background. It travels in the same momentum direction, but it picks up a different flavor. So there is a flavor changing term, but the same momentum, the same everything else. So the initial state and the scattered amplitude add up coherently, and that's how you can have off-diagonal, flavor off-diagonal terms. So the electron neutrino changes its flavor when one of the background neutrinos are kicked into this mode. Now there is this oscillation Hamiltonian, where for this neutrino you write terms proportional to all background modes which exist here. So the note is that the flavor state of the background neutrino explicitly enters. So it means that flavor states of these different neutrinos are coupled. The number density in a given mode enters. G Fermi is sort of the same thing you expect from the MSW effect. And then there is this angular factor, which simply means that when things go in the same direction, auto-relativistic things, they don't see each other. So neutrinos have to make a certain angle with each other to have a large enough amplitude. So this is a rich many-body phenomenon. It has many regimes. The simplest example that I think is very instructive is in this toy model by Georg Rofelt and Alexei Smirnov. This is not time causal because they're really the first paper that showed that there are large transformations were done by Huayu and Yon and George and Joe Carlson, but their case is just more complicated. So it's easier. This is a follow-up work. It's easier to understand what's going on. So you create a bunch of spins. They are initially strongly self-coupled, and they are in a certain superposition of states. When they are initially strongly coupled, they will remain strongly coupled, and they will precess around the external field, which is provided by the vacuum term. And then when the key is that you relax the neutrino self-coupling, corresponding to the statement that as the neutrinos flow out, their self-coupling decreases. Then you ask, what is the final state of the system? And the system does the following. So it started as a coupled state, and then some neutrinos change flavor and become electron neutrinos, and others change flavor. Sorry, some go to the electron neutrino state, and others go to electron antineutrino state. And this problem you can do in Mathematica in a few minutes, and convince yourself that in the end, the spectrum that you get will have a strange feature where you split the spectrum at lower energies. You make all electron neutrinos. At higher energies, you make muon neutrinos out of these guys. In the spin language, the following happens. You have a bunch of neutrinos initially strongly coupled in one object. Then when you decouple them, and this picture actually is given in the original Duan et al. Paper. When you decouple them, then they stop being in a single object, but then some of them go up and some of them go down so that the flavor is preserved. And this is just a dynamical statement about a system of spins being relaxed in this way. Now, the next toy problem is you consider neutrinos and antineutrinos. And this is closer to what is found in the realistic supernova calculations. So initially, the oscillations are not suppressed, and at some point, this system, the instability in this system is triggered. All antineutrinos then go into the mu and tau state, and some electron neutrinos go to electron neutrino state, and some go to muon neutrino state. And again, there is a split. This process can be understood by considering the dynamics, some equations which I don't write. You started with the spectrum where you had electron neutrinos and electron antineutrinos. All of these guys will be converted, and most of these guys, but not all of them, will be converted to another flavor. So at the end, you get this wedge of electron neutrinos, which is this sort of the simplest split phenomenon, where you have a spectrum with an abrupt feature. So these features are nice because they can be, if you find something like that, then it's certainly not explainable by thermal physics at the neutrinosphere. So you discovered this nonlinear physics of collective oscillations. Now here is an example of neutrino collective evolution in another regime, and I plot this on the sphere of flavor. And again, I have up is electron, and down is the non-electron flavor. And I just let this run, and it does some pretty crazy motion. And this is not very difficult to do. This is in the single angle approximation, mainly because this way I can plot them. So it goes through some regime where this jump rope extends and then contracts. And after a long evolutionary trajectory, it starts splitting into different components. So some neutrinos will go up and will remain electron neutrinos, and some will go down and will be converted to the non-electron flavor. So this is what distinguishes, I mean, to show this is just to show that there is a qualitatively different problem when you have collective oscillations compared to the standard MSW, where you just rotate one spin with an external magnetic field. So let's see, I don't know. I can talk until the end of this talk while this movie finishes. So it does that. And you will see. So eventually, some of these guys go up, some of these guys go down, and this will give you a spectrum with actually several splits. Right, several splits at different energies, which is an interesting dynamical phenomenon. So let me skip that. There is another calculation which you can do, where you assume a different spectrum. There is an oscillation, and this oscillation looks quite different. I just want to say that there are different regimes. So since I'm almost out of time, I want to summarize things which are known. So we have to deal with the standard MSW effect, at least in the first second, where you have the profile is smooth. This standard MSW effect happens when delta m squared over 2e is comparable to the density of background neutrinos. Then we have to add to that the effect of turbulence when this bubble, turbulent bubble, expands and the densities there get close to resonant. And there we need density fluctuations on the scale of the neutrino oscillation length. And then the third effect is that you have collective oscillations where you transition from strongly self-coupled regime to the vacuum regime. And again, this is a relaxation phenomenon where the coupling of the neutrinos becomes comparable to the delta m squared over e, and this is where this magical process happens. Now, there are many exceptions to this picture. I can keep talking until somebody tells me not to. So here is one interesting phenomenon. So I mentioned that the transition from that collective oscillations start when self-coupling becomes equal to the vacuum potential. But is that always true? Because you could have, in principle, a priori, you could have large oscillations when you have strong self-coupling, stronger than that. But that would be a problem, or at least it would be very alarming, that you have oscillations close to the neutrino sphere where you release your neutrinos, because then you can ask, do I have these collective oscillations inside of the neutrino sphere? Then I have to re-examine my supernova models if there are strong collective effects. Now, this question is not completely settled in my mind. I don't know that you can always prove that there are no collective oscillations at or inside the neutrino sphere. In fact, in some cases, it's probably you need to do both. But at least in this late time case, we were able to show that if we do calculations properly by including multi-angle effects, the oscillation does not start until about 120 kilometers in this model. Whereas in the single angle approximation, the moment neutrinos are released, they began oscillating. So this is crucial for the validity of supernova models. And it's also crucial for nuclear synthesis, because if you have large flavor change where you have the neutrino-driven wind, that could affect the neutron-to-proton ratio and therefore the yield of nuclear synthesis. There is another set of effects that has to do with the three-flavored nature of the problem. So I've been showing you these two-flavor cartoons, and this field indeed started with two-flavor calculations, at least to understand what's going on. And now everybody does three-flavor results. But here is an interesting phenomenon. So if you take a two-flavor calculation, you get some spectrum. If you add a little bit of delta m squared in the solar channel, but a very small value, so 1% of the standard value. You don't expect that to do much, but it turns out that the spectrum that you get out is completely different. And that's because the trajectory, the evolutionary trajectory, can be unstable if you consider the full three-flavor space. If you artificially confine yourself to a two-flavor trajectory, you get one answer, but the moment you add additional degrees of freedom, you run away somewhere else. Now, this has the same kind of a phenomenon has been seen more recently, and this is very relevant to the topic of this workshop because this involves very elaborate calculations in principle to get this settled. So the idea is that these authors considered instabilities in the direction where axial symmetry is broken. So people imagine that in the standard multi-angle, or in the original multi-angle calculation, you consider a spherically symmetric distribution, and you assume that it remains spherically symmetric. These authors wanted to argue that if you consider the azimuthal degree of freedom, for some spectra, the symmetry is broken spontaneously by the evolution. Now, this was done in the linear stability analysis. Nobody knows actually what happens as you study this numerically, but it's clear that you need many more degrees of freedom because you need the azimuthal angle, and then you also need the direction. So this is an outstanding problem, but at least it shows you, gives you the flavor of what can go on here. If you add additional degrees of freedom, sometimes the system spontaneously runs away somewhere. Now, one last thing that I want to mention is what happens if you have the neutrino sphere and collective oscillations close in. So what I showed you before was that the neutrino sphere was neatly here, and all collective oscillations were happening here, and the MSW was happening here. But in the first second, when you have this accretion phase, the density distribution is more like this. And with this density distribution, the scattering above the neutrino sphere is non-negligible. And these guys, which scatter, they enter the Hamiltonian with a large angle. So graphically, this is what happens. You have neutrinos scattering at a large angle, and then they enter the Hamiltonian with this large angle, so they actually dominate the oscillation Hamiltonian. Nobody knows how to do this problem because the matter distribution in these calculations is extremely inhomogeneous in both density and chemical composition. And the worst thing is, perhaps the worst thing is that neutrinos here can scatter backwards, And so then we're not solving the initial value problem that we had before. We're solving potentially a boundary value problem. So this is relevant to understanding the neutrino signal during the first second. And this is perhaps somebody in this room will solve this problem. But it requires extremely, it requires super computing. It requires many degrees of freedom to do this right. There is one case where this can be computed, and that's during the neutronization burst, when the density distribution is still spherical. And you can show, and this was done by JJ and collaborators, that you can consider the case of the scattered halo versus just the standard treatment of a neutrino bulb, and convince yourself, at least in one case, that you get a different spectrum by comparing the two calculations. So fortunately, I'm out of time because I can speak more. So there are several directions here, and one direction is purely experimental, but it's very important. We need to understand this physics that we are computing from these different oscillation effects, what impact it could have in terrestrial detectors. Now this is tricky because, as I said, we don't understand all the problem from beginning to end. But at the same time, you have the LBNE collaboration, which is designing their detector now, and they would like to make design decisions that will put them in a good position if there is an explosion 10 or 20 years from now, because the decisions are for the design are being made now. So then there is that work. And another work is understand how these flavor transformations impact nucleosynthesis and perhaps the explosion itself. So these are these are applications from the point of view of the oscillation theory, but they are very important applications, and there is time pressure on these. And then on the theoretical side, since there is a zoo of all sorts of phenomena in this problem, what we would it doesn't seem that we can treat this problem end to end given the world's computational resources. And it doesn't appear that we can solve it and give you a universal answer. But what is needed is we need to understand the different physical phenomena that exist in the system, some of which I tried to highlight. And then this will inform us how to structure our future simulations. Now, qualitative understanding, when something matters, is very important. So I think I should quit here. I have, in principle, many other things to discuss, but I think this is a good motivation for people to think about this. I mean, this is very enjoyable from the theoretical point of view, and also as a computational challenge. This problem will remain at the forefront for maybe several decades. I don't know. Thank you. Questions, complaints? That's actually a very good point, which if you have this modulation, for example, right, in the ice cube detector, and you can say, well, maybe I'm seeing just the modulation of the accretion rate from SASI. But maybe also I'm seeing collective oscillations which proceed in this changing profile with plumes scattering neutrinos which change as a function of time. The short answer is there is no short answer. And right, so there's 50 millisecond or so time scale for the SASI to slosh around. And the turbulence inside, seems to me, has quite a comparable time scale from your movie. And then, yeah, there are a variety of time scales. And, you know, before halo, which is when that paper was written by the Munich group. Before the halo effect, they said that if we see these oscillations, it surely is modulating accretion rate. I'm not so sure. So, but it could still be the presence of SASI, but just through a more complicated mechanism of collective oscillations, not just the accretion rate. Right, that's right. Yes. So the short point that I want to make is right now, the first second, when you have the accretion phase and you have all this wonderful stuff happening, is theoretically largely unknown what you will see. For neutrino oscillations.
I agree completely.
Yes.
I mean, we don't really even know how to begin to model some of this physics, as you well know. Yeah. And I think, one of the messages that you're making, one of the lessons you're trying to teach us here is that for flavor oscillations, we may need information that somehow the modelers have kind of de-emphasized. So we need to know composition, for example, the halo effect you talked about. Composition and during the accretion phase.
So from my perspective,
Oh, good, fantastic. No, please.
so my perspective, the supernova problem, progress on the supernova problem has been achieved by layering 1 dimension to 2 dimensions to 3 dimensions, Newtonian to GR, etc. So everything that I'm going to talk about this week, of course, is based on zero neutrino mass. But ultimately, the models have to be extended to include non-zero neutrino mass in the full sense that you guys, right?
Mm-hmm.
Vacuum and MSW, but
Yes.
neutrino
Mm-hmm.
collective oscillations.
Mm-hmm.
Now, from my standpoint, that's a no-brainer. But as George just said, the theory, the equations for that are only now, they're not there yet.
No, the equations are there. We just there is no supercomputing power to solve them.
Well, I'll get to that.
Yes, very good.
But the equations themselves, we are still developing. George and YU and Chen and Alex, you guys are the experts. They're still developing.
The basic equations we have.
Okay.
The basic equations.
All right.
I mean, okay, collisions and oscillations, if that's what you mean. There is some. No, right.
We think we have those.
Yes.
Okay, good. Then I worry about, so George tells me the resolutions that are required, the angular resolutions that are required, for example, when I plug those angular resolutions into the spherically symmetric case, I have an exascale problem.
That's right.
Okay?
Mm-hmm.
So what I think would be helpful for us, it's not that we don't want to do this, but it's hard enough to do it with zero neutrino mass, but that what would be helpful is somehow cull some essence of the physics that can be deployed even now, if not on the exascale, in a decade. Because we are not going to be able to solve
That's right. That's right.
Mm-hmm.
Mm-hmm. Mm-hmm. That's right. Now it's possible that such a useful simplification can be done. It's also possible, based on the lessons that we've learned so far, that sometimes these simplifications, they seem to be valid until you see that they're not. So this was the one example that I showed, that after the first several years of discovery of these spectral splits, people said that it's mostly okay to treat this problem as a single angle problem, which means that you take some average coupling between different neutrino rays and you plug this into your code.
Although in fairness,
Not in your paper, not in your paper.
indicators of
Yes,
single angle
yes,
approximation,
yes,
this guy and
yes,
I
yes. No,
actually
so that's,
never said that.
so there, no, but there is actually, that's right. But not only the two of you, because in your 94 paper you said that it's explicitly important to treat multi-angles, but even in your 2006 paper you said just because they look the same for this case doesn't mean that they are the same. But other people said no, 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 it means that they are the same. And for the first several years, people considered this single angle calculation in most of the treatments until, well, several papers, but this is the one I like, a completely unbiased choice, where you can you can consider a single angle calculation right at the neutrinosphere, and you get that there are flavor transformations at the neutrinosphere. And then what you're saying, you know, if you take this thing and you put it in a bigger code, then you discover fantastic things in your code. And then when you do a more complete treatment, taking into account the dispersion of neutrino interactions on different rays, that effect disappears until much later. So I understand that there is a need to make some toy approximation to make the problem treatable. Just that this toy approximation may also miss some effects. So it's going to be a fun problem for many, many people for many years, I think. Mm-hmm. Right, right, right. Mm-hmm. Yes. Mm-hmm. Yes, yes, yes. Yeah. The question is, what's the biggest simulation you can run and how to capture the essence of this? Yes. Mm-hmm. 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 Mm. Right. I'm just saying that there is a particularly bad time during this explosion, during the accretion phase, where everything seems to be a mess and we don't know how to do this problem yet. But at a later time, when the shock is pushed out and you hope that oscillations and neutrino transport decouple, at that time, it's still very valid to ask what are the transformations and what LBNE should see. And for that, both fluxes, the angular distribution of energies on different rays, and the spectrum of this turbulence are extremely important. Now, here is where I have a request, right, which I already made, that people who consider explosions, they typically stop when the shock starts to move out. And then people who consider late time propagation of the shock typically remap it in a spherically symmetric way and then continue. And then even in that case, Janka and his group found that there are plumes of turbulence that form. But there should be even more if you just take this violent convection and you let it expand. So that would be a very interesting simulation to have. I understand that the difficulty is in the core of the neutron star. Your time step gets very small or something like that. So a simplification there, so you could follow large plumes to larger radii to 5 seconds, would be extremely helpful, right? Because in that case, you can go and make a prediction to LBNE, and they can go look for it. That's right.
you've got to go to, for the
Yes.
general case, at
Mm-hmm.
12 solar mass, it's done.
Mm-hmm.
But when you get up to 15, 20, 25,
Yeah.
1.5, as I'll show tomorrow, they're not done. So you've got to go to 2 plus or something like that
Mm-hmm.
before you can then say, okay, the explosion is generated. I've got this in dynamical environment.
Mm-hmm.
Let me decouple, pull out the proto-neutron star, set up a new problem, and follow it.
But just to give a flavor, right? So if you can run to these late times, and these are simplified things, if you can run to these late times when you have turbulence and shock and collective oscillations, then you could get things of this kind. So it's some calculation that I did for the LBNE experimentalists. So you can combine the shock effect that I said in the beginning, turbulence in the bubble, and collective oscillation in the bubble, assuming the transport part is decoupled. And then you observe this feature, which is non-thermal, which moves to higher energies as the bubble expands. Now, if the LBNE detector can see something like that 15 years from now, this would be fantastic. But, you know, so this is a smoking gun thing. It doesn't matter what you do at the neutrinosphere. You don't get these moving sharp features. But again, to make a more complete calculation, it would be good to know what the density profile does at 3-4 seconds, and more self-consistently. Because right now, you know, we steal this information from various people who never intended it to be used for this purpose. LBN in E or F, yeah. So the time resolution is pretty good, I mean, for the purpose. I mean, this time, over some slice of time, right? So there'll be like half a second or maybe a third of a second time slices where you can take these spectra, and then of course, so this is done in a 1 second average. But you know, again, it depends on the progenitor also. Like if you have a progenitor which is light, then this feature looks very different than if you have a massive progenitor, which doesn't explode, as you say. So